Well, thank you, Sharon, and thank you all for attending today. Very excited to be presenting in this the time of uncertainty and what's going on in the world. This is about as good as it gets. But today we're going to talk about latest on laser flow. And what we're going to discuss today would be measuring flow in some difficult applications or conditions. As Sharon mentioned, I am a business development manager for the Water Platform Group, and probably have spoke to many of you over the years, but you can always reach me at the email below, rick.dye@teledyne.com. And feel free to reach out to me anytime you need to, or if you have any questions, I'd be happy to help you. We also have a good group of application people at the factory that can assist you as well. So feel free to give us a holler anytime we can be of assistance to you. Okay, so let's talk about what we're going to learn today. What are some of the challenges reading open channel flow? And look at that. Well, one thing we need to know is really, how does area velocity work? What are some of the expected accuracies that you should see out there from different technologies? And I'll kind of go through that a little bit with you. Why does the laser work in these kind of applications? What makes it different? And how is this going to save you money? And obviously there's a lot of things going into that, which is non-contact and not having to have people go to the field, shut down roads and those kind of things. How is the sensor installed? I have some pretty good pictures that give you an idea of what we expect, or what you need to expect when you go to install one of these. And then what are the maintenance requirements? What do you think you're going to need to have to do? And so you can kind of plan for that. And I'll show you some of the tools that we have in the meter and the sensor that will give you some very valuable diagnostic information to help you make that determination. And then we're going to talk lastly about some of the intrinsic safe rating capabilities that we have now with the laser. Okay, so this one, some of you may have seen this slide in the past, but this is the ISCO Flow Measurement Lab. We're very lucky to have this, and this is really used to help us develop and improve our flow technologies. We're one of the few, I think, in the industry that have such an elaborate system here, but we can go from 4-inch to 24-inch pipes, and that makes it very, very useful to run a variety of different types of applications. So we can, again, further enhance what we have developed. So why do we measure flow? A lot of different reasons, but some of the most common: inflow and infiltration, or INI studies. And if you're from Europe, they are considered flow surveys a lot of times. Enforcement requirements, industrial pre-treatment. So they're billing people out there and for what they discharge, and they need to measure that flow so they can get an accurate bill. And then finally, hydraulic modeling is another big one in the collection system. And they're using the flow data to help them tweak and improve their hydraulic model. The other one would be billing or water custody transfer, as it's sometimes referred to. And these would be cities discharging to another wastewater treatment plant. Some good examples would be cities like Atlanta, Phoenix, Milwaukee, Boston, Denver, you name it. Just about everybody that is monitoring or measuring their flow and being billed for it has to know accurately what their flows are. Okay, let's talk about some of the equipment options now. On the left, you'll notice that is a signature flow meter. A lot of you have seen those. They've been out now for quite a few years. A very, very popular one for more permanent. The one on the right is the 2100 series, which is going to be a more portable unit. Really what you're looking for, though, is how are you going to power this? What are your capabilities? Do you have AC power? Do you have DC? Maybe you have batteries, solar. We see a lot more and more of those types of applications. So you need to be able to determine that. And then again, meter, are we going to be permanently monitoring this? Or are we going to do portable monitoring? And permanent would be more signature related, although signature can also be used in a portable application. But normally in a portable, you would be looking at more of the 2100 series. So let's look at what is the signature. Many of you may not be aware of it or familiar with it, so I'll kind of briefly go through that. But the signature is what we refer to as a smart device. All of our sensors now are going to be smart sensors, which means they have their own microprocessor built into them. So they process the data and the readings actually internally in the sensor, and they send it up the line digitally to the smart device, or in this case, signature. You'll notice below the signature in this picture is a lot of different meters, a lot of different sensors. So we can do ultrasonic, bubblers, lasers, SDI-12 Modbus input if you had a mag flow meter, for example, something like that. So we can take a lot of different technologies, bring them in. We can also output a lot of different things. And one would be like the internet. And you'll probably, if you haven't already seen it, FlowLink Cipher, which is our latest, greatest internet cloud-based program, which we're very excited about. That would be one of your internet capabilities, but alarms, USB devices, plug and download, which is what you can do with Signature. FlowLink software, also Modbus or SCADA. So if you want to take it out to a SCADA system, you can do that. Ethernet is another popular thing for an in-plant type of application, or the traditional tried and true analog output, 4 to 20 output. So this might look familiar to many of you out there. This is a 2150 area velocity flow module, workhorse of the industry. We've been selling these since the late 90s and has been an amazing product for us. And that thing is, again, a very popular flow meter, flow logger, flow module that you'll see out there. And they use those a lot for inflow and infiltration studies. So let's talk about how does area velocity flow measurement work. In a nutshell, Q is your flow, and flow is equal to the area of flow, or the wetted area, some people call it. And this is done using a level measurement technique. One way to do it would be a pressure sensor, and another common way would be an ultrasonic sensor. So we know the area based on these measurements, but then the next component we need would be the velocity component. The velocity typically in the industry now is primarily Doppler. The old police radar gun. We transmit a known frequency, we know the return difference, and we can calculate the speed. There are a couple types we're going to talk about, but one in this case is the contact, which when I refer to contact, I'm referring to a ring, a sensor on a ring that's in a pipe. And these are the most common ones that you would see out there that have been around for many, many years. And this picture up here gives you kind of a good example of what this thing actually does. So you'll notice the level measurement is that blue line. So it's sensing the pressure over that sensor, and it transmits a frequency out the nose. Everybody has a little slightly different frequency, but that's what it's doing, transmitting, getting a return signal back, and doing an average of what comes back from that measurement. On these types of sensors, what you can expect as far as accuracy goes would be if you're within a roughly 2 foot depth, 1.5 to 2 feet, you'll be in the 5 to 10% range normally if you have good hydraulics. What we found though is if this flow gets deeper and deeper, the sensor will tend to underestimate the velocity because it is reading towards the lower part of the flow. So with peak velocity, as that water goes up, the faster velocity will follow closer to the surface. So that's the reason that you will may underestimate some of the velocity on that. Okay, so why do we use a non-contact flow sensor? Obvious reasons, and this is one of them. It gets covered. I don't care who's manufacturing this sensor, it is not going to read. So what we try to do is really evaluate your system and your needs. We have a lot of reps and distributors out there throughout the world. They are very trained and capable, and they will look at your application and to determine what is the right product. So what we're going to be talking about though today is going to be primarily the laser flow. So let's look at the principle of operation. How does this thing work? It has an ultrasonic sensor that's mounted in the back, and it has a 10-foot range. So it can be 10 feet above the minimal flow. So sometimes people have them in bigger pipes than 10 foot, but the flow cannot be greater than 10 feet away from the sensor. We also designed this to be a what we would call a zero deadband sensor. What I mean by that is every ultrasonic will typically have about a 1 foot deadband, including ours. So what we did is we put that at the back of the sensor. You'll also notice it's angled. And the reason we did that was so that any moisture that's in that manhole that collects on that sensor face will just run off the sensor. You won't have to go in and do any kind of maintenance, typically with the ultrasonic sensor. So whether it is submerged and becomes unsubmerged, and you should not have to clean that. Okay, so now we get our level measurement, or we know the distance. Now we measure where the water. So once we know where the water is, what we do is we will transmit a laser beam into the flow. The patent of the laser, and what makes this unique over other technologies out there that you might be aware of, which are surface velocity, we are actually reading below the surface of the water. So this is our patent, and again, very, very accurate way of measuring, and very excited about how we do that. Like any other Doppler device, we know the frequency that we transmit, we know the return frequency, we can calculate both the speed and the direction of that flow. All right, so let's talk again, give you a little different look here. This is a side view, a front view. Again, both are doing the same thing. We're measuring the distance to the water. Once we know where the water is, we focus that laser. I like this picture because it gives you a better idea when you're out in the field installing one of these. If you put your hand underneath the laser, you'll see a dot the size of a quarter roughly. Where it hits that water, you should see a very, very tight laser point. If you do, then all is well, and it's going to probably read. If you don't see a very tight point, then something isn't right. It either doesn't know where the water is, or maybe a program error. This is known as what we call the converging section or point of convergence. And what's pretty interesting about this, or unique about laser, it takes 5,000 velocity readings, and it does all of that in 2 seconds. So by comparison, a regular area velocity takes 512. Laser takes 5,000, and it does it in a very, very short amount of time. Okay, so another one, this will give you a little better idea kind of what this thing is doing. The laser is actually mounted inside, so we move the laser to focus where we want it to focus. So that's how we are able to achieve that very tight point and get the reading that we're looking for. We know the frequency transmit, we know the return frequency shift. We can again detect both the speed and the direction of the flow. Okay, some of the other things we do that's pretty unique would be the velocity diagnostics. And what this is, without getting overly complicated, every time the laser takes a reading, it takes 5,000 of those, and the more that agree on the return frequency or speed, the bigger this signal is. So you'll notice on the bottom, it says 2 meg, 4 meg, 6. That is the frequency return or the speed of the flow. When I look at this, what's important is anything over roughly, my experience, 500 on FFT amplitude on the left means we're getting a good reading. So in this case, I have a lot of readings that agree on the return signal or return speed of the water or frequency. And so I have a very, very good, accurate signal where it's looking. So like that, and this is one of the, again, things that we use quite often to be able to verify that, yeah, this thing's working or it's not. The other thing that's important about it is right above that circle, you'll see X angle, Y angle. And what those are telling you would be the pitch and roll of the sensor. So the sensor has a built-in accelerometer like a cell phone. It knows where it's physically positioned. And as a general rule, anything on the Y, which is a 45-degree angle, anything, if you're plus or minus, well, we want to be 45 plus or minus 3 degrees. Every degree off of 45 is theoretically about a 1% error in velocity. What's key about the laser is that the laser will automatically compensate for it mathematically if it did shift, if they didn't get it perfectly installed, or if it went underwater and it moved the sensor slightly. So very, very good diagnostic stuff. This is all stored in all of our meters. So this now is another kind of look. And what we look for right here is it's all about signal to noise ratio. So any technology out there that you might be using, we gotta know what the real signal is compared to the noise. And this is the challenge with anything. And what you'll find with the lasers, our signal is so clean that our signal to noise ratio is um, incredibly clean and accurate. What that means to you is as this water slows down, if you get into real low velocity applications, this peak will shift to the left. As it moves to the left, that's where the slower velocity is. Because that noise floor is so low, we are able to read, again, very, very slow velocity. This is stored in memory as what we call Doppler power. You need a minimum of 1,000 Doppler power. So a measurement really of the quality of the water that you're getting, or the velocity reading that you're getting back. So there's multiple ways of setting up a laser, and this one's kind of showing you the full-blown way. Bottom left kind of give you an idea of what that laser looks like. You can mount it on the front wall, the back wall, we don't care. It can be pointed upstream or downstream. You can also set it up so it can do either a single point. So right here, I'm doing an ultrasonic level measurement. Once I know where the water is, then I can do actually a multi-point, which means I can scan horizontally and vertically, total of 15 points. So it's going to do the top row at a certain percent below it. It will do the middle row, and then again, the last row. When we set it up like this, we are taking 75,000 velocity readings, and we're doing that in roughly a minute and a half. So why would you do this? Why wouldn't you always do this? Really, it comes down to time of reading. So if I have a pump station application where my flow is rapidly changing, maybe this isn't the best thing for you. You may only want a couple points. If I have batteries, I may not want to run all these. If my flow is uniform and all the readings are close to the same, then you may not need it. It doesn't hurt anything to have them on, but you will sacrifice a little bit in time to get the reading and as well as power. All right, so how accurate is this thing? We went through multiple third-party tests. We've also went to the UK and did tests over there. It is an MCERT Class 2 rating. It is 4% of reading is our specs. So as far as the non-contact goes, it is the most accurate specified non-contact area velocity meter. Third-party test results. So we did a lot of testing again with these. One is the Irrigation Training and Research Facility at Cal Poly San Luis Obispo. We found that we were about 1.8% error. So very well respected facility out there on the West Coast, but we wanted to go somewhere on the East Coast. So we picked Alden Research Lab. A lot of you know those guys. And again, another very, very well respected laboratory, flow lab. They're in Holden, Massachusetts, and we were 2.7% on the absolute error. So everything we've ran and compared to has been really, really, for the most part, very, very encouraging and very, very accurate. All right, so let's talk about what we designed it for. Initially, we designed it looking at large pipes, and we refer to anything above 36 as a large pipe. Why do we design for that? Well, obviously, nobody wants to get in that flow if they can help it. So giving them a good, accurate method of measuring flow without going in was a goal of ours. But we also looked at small pipes, anything less than 36 inches. What I will tell you now is that we are selling a lot more into smaller pipes than I think we even thought we would. Why is that? A lot of them are in 4-inch pipes, 6-inch, maybe industrial pre-treatment. So they're looking at, I have no flow or very little flow, and then they batch dump something, and now all of a sudden I have a lot of flow. So the laser is able to read really all those conditions. Okay, so let's look at some of the applications that are challenging, difficult, high velocity, low level. And we see that with steep slope pipes. There's a lot more of those out there than I thought there was. Low level raw wastewater. So anytime you get down to an inch, most sensors will not read that, and they need at least 1 inch to be able to even start taking readings. The other thing that happens when you get down below an inch is you're looking at a lot of ragging and debris issues that are going to require maintenance on a standard area velocity that's on a ring and a pipe or a contact sensor. Slow velocity, another one that's really difficult. Anything less than about a half foot per second is going to be very, very challenging for anything to measure. The laser will read, our spec is a half foot per second, but there's a lot of times where it'll read much, much lower velocity than that. We see these a lot in residential collection systems. So trailer park discharge, they need to measure that. Or maybe they're doing personal property I&I tests or studies. So different ways that people are trying to measure that. Slow and clean is another challenge. Wastewater effluent, wastewater treatment plant effluent can be challenging because hopefully if they did their job right, the water is going to be very clean. Chlorine contact or UV disinfection channels are another one that are very challenging because again of the nature of the flow, very slow and very clean. We are doing some stuff with drinking water influent. This is kind of exciting. That's a little different twist than what we were initially targeting. But we had a plant down in Kansas that was looking at a very wide rectangular channel. They actually put 2 lasers on that. It's raw water, so it's coming right out of the ground, but it's a challenging application, not a lot in that water. Stormwater is another big one. Why? Because there's a wide fluctuation in flow. Nobody wants to put anything in the flow if they can help it. And a lot of times your channels are not your nice uniform channels. They are going to be irregular shaped and can be also very, very difficult to measure. So let's look at this one. Here's one that's a low level, high velocity application. In this case, what we need with the laser is we spec a 1/2 inch minimum depth for velocity, and we can read up to 15 feet per second for maximum velocity. So the one on the bottom right was actually Duluth, Minnesota. They were trying to measure that flow, and that water's coming off the hill and it is screaming. So really, really challenging to put anything in that flow. Okay, here it is. Now, when we installed the laser in this application, you'll notice that you're not in the flow. It's an easy install for the most part. There's 2 bolts that hold it in. You'll notice there's a handle on the top. And what that's designed for is you can use a street level installation tool to remove and install that laser once you get it installed. The tabs on the mounting bracket are designed so that you can easily nestle that thing or nest it back in place after you're done. So here's a good example of a really, really challenging application. On the second pane here, you'll notice that average velocity was right in about 13 feet per second. So incredible velocity. How you measure that is nothing less than almost miraculous that you're able to pick that up. But very, very challenging. If they need to measure it, this is about the only thing I know of that will do it. Okay, slow velocity application. This one on the left is using a temporary mount bar. And so you just jack it across the channel. You'll see the laser dot on the flow there. I'm seeing more and more of these types of applications, very, very slow movers. And anything, again, below 1/2 foot per second, now you start getting your signal into your noise. And that's the signal to noise ratio I was talking about earlier. So when you get down into this range, it's tough. Your signal has to be very, very clean. And most cannot pick that up. So they can't pick the signal out of the noise. Why can the laser do it? Well, as I showed you, we have a very high signal to noise ratio. So it is now able to pick up these extremely low velocities. And again, the spec is a 1/2 foot per second. We will guarantee that. At times you may find it's lower than that. We don't really guarantee below that, but if you did a demo and put one in, we will know immediately if it's going to work down there. But we do have applications where it's read even much, much lower than 0.5 feet per second. So in this one, this is some of the data. You'll notice the dashed line is the 0.5 foot per second, our spec. And you can see velocity was down well into the 0.3 foot per second range. So the laser did an incredible job reading that. Okay, so now another way to install these things, we get asked that all the time. In open channel, that's no big deal. But if they have a closed pipe, really all they need is a small opening in the top. The one on the left is the ISCO Flow Lab, and you'll notice that's what the laser looks like when it shoots into that opening. So when we're doing industrial monitoring, we're seeing this kind of application more and more, which is ideal. If you can do this, this is perfect because now we're reading level right below roughly the handle, and we're reading the laser velocity right in that pipe. So now we have good hydraulic conditions. We don't have somebody that grouted in an invert that's maybe not perfectly symmetrical. So this gives you a much better accuracy condition. Here it is again. You can see the laser dot on the water. 2 bolts hold that bracket on the wall, so very easy install. So wastewater treatment plant effluent. So here's a couple of them here. And you'll notice sometimes there's foam on the water. There could be air bubbles and trained air. The one on the right is kind of an interesting story, and that's why I'm bringing this up. This was one that was very, very challenging. They have a lot of entrained air on the top, very clean water. And so are we going to work? So my rep out there called me, Rick, is this going to work? I said, don't know. Let's put one in. We put one in, and what you'll notice right here, we had drops in velocity. And so it's like, why are we getting those? These are not actually going to zero. They're going down to about 0.5 feet per second or slightly less. So then we grab the diagnostic. This tells the whole story right here. And what this tells me when I look at it is the frequency, which again on the bottom is the speed of the water. We have a great deal of low frequency or low velocity returns down there at the low end. And then at the upper end, we're seeing the real velocity. So this is what we really wanted to measure, but we were picking up some of that stuff on the left end. So what we were able to do is go into the software and just say, you know what, I want my minimum velocity to start at this point. And what that did for us was, without doing any changes to the site or the application or any construction, all we did was made that one minor change in the program, and now the data looked phenomenal. So everything past that that bar at in the middle was after we made the change. So great, great application, great story, and again, before and after. All right, so let's look at some other ones. So here was one I'd like to show because it was a kind of a challenging location to install. Rectangular channel, high velocity. And so what they did was they just cut out that opening in the top, put the laser, mounted it just like that. And for now, they were looking for just a temporary test to see how well it was going to work. And this test went quite well for them, but it was easy to do. All right. So if we don't have good conditions on our pipe, or the water is free falling out, like in the picture here, we were going to have a problem before, because with the initial laser, it was going to read the level right below the sensor. And in this case, you would see it would be dropping out into the channel. That wasn't going to work so well. So what we were able to do is, now you have to order it this way, but if you order it with a remote ultrasonic sensor, you will see that now you can mount it up into the pipe itself. It mounts either vertically or horizontally, preferably horizontally, like you see here in the picture, and reflects off a stainless steel deflector. Hits the water, we know where it's at, and then we use the laser to read the velocity in that channel. So the picture on the far left is a wastewater plant influent in Washington State. The picture to the right is a combined sewer line in Iowa. All right, so let's look at some more challenging applications. Here's one. They didn't have a lot of room, and so they needed to measure that. There was a small opening in the top, so you got kind of constructive or creative, put that rebar across it, and now they're able to measure that flow very easily without anybody trying to go down in there and install a ring. Here's another one that's always difficult, is coming around a bend. This particular one isn't horrible. I've seen way, way worse. But in this case, what they were able to do is mount an ultrasonic, remote ultrasonic, right over the pipe coming into that manhole. And then the laser could be mounted backward or back a little ways from that opening. And now they're reading exactly in the same point. So even with the bend in the pipe, they're able to use the laser for that. And this is one of my favorites. This is in Istanbul, Turkey. They were trying to measure that flow, obviously quite dirty flow. Didn't want to get down in there. Nobody wanted to be in that pipe. And so they're able to use the laser with the remote ultrasonic to measure that. Okay, here's another one that we're seeing a lot more of, which would be a monitoring a river or river application. A lot of times you get some real high velocities in there, and those are dangerous and challenging as well. So why? Well, in this case, this site normally runs dry until they have an event, and then it'll go from either no flow or very low flow to pretty much raging rapids, as you can see in this picture. And you don't want sensors down in there if you can help it. You don't want cables hanging out of the water. Um, and you could have some inaccuracies, again, due to your velocity measurement techniques and technology out there. So as I mentioned earlier, the continuous wave Doppler style meters are very good, but as that water level gets deeper and deeper, they will tend to be less accurate as the flow goes up, exceeding about 2 feet. So you need to determine what your accuracy requirements are, and do you want to put a sensor with a cable in there? Benefits of laser flow. It can read both slow flow, so it can read your baseline flow, which is either very low or no flow. And it can adapt easily to the high flow conditions. So as your water level comes up, it knows where it's at, it knows where the peak is, and it knows where it wants to focus the laser. So beauty of it is, again, very accurate to the entire range of what's going on. And nothing is in the water. So this is hanging off a bridge. Going to have very few people that are going to want to do any kind of vandalism on it unless they want to climb the bridge, but also nothing is going to tear it off or tear it out of the channel like a sensor with a cable. All right, so let's talk what happens when we go underwater. The laser is designed to handle submergence, and it is 6 feet, 72 hours, excuse me. And you'll notice another thing in there, the design was that we would have like an air pocket in here. So as that water level comes up and submerges the sensor, it will be like a diver bell. So it will keep the water from getting all the way up to the window. Now, having said that, if it did happen to get splashing or something up in that window, the laser has what we call a optical clarity system. What that does is that detects backscatter of laser light coming into the laser. So if it fogged up, if I had it in the back of a truck and it's 20 degrees out and I put it in a manhole, it could want to fog up like your glasses. Also, if it did submerge and you got splashing, that could cause you potentially some issues. So we came out with the optical clarity, and so now it will turn on a small window heater, warm the glass, and problem solved. But again, the diagnostics that you look at will tell you if you need to do anything to this sensor at all. Once it does go underwater, though, we have a continuous wave Doppler sensor on the bottom. So this has two sensors, basically a pressure sensor that's on the bottom to read the depth of surcharge. It has a continuous wave Doppler velocity sensor in the nose. So it transmits, knows the frequency return, knows the speed of the water. So now we're able to measure all the way through submergence. And when it comes back out, it will seamlessly transition back to laser. So if you have this on an analog output, you can have it so it will have one continuous analog output that will seamlessly transition from one technology to the other based on the conditions. All right, so stormwater. Here's some kind of good pictures for you, I think. One on the left was something we did a test, and we just used some clamps to install it in that application. The one in the middle is the same look, only from the inside looking out. And then the one on the right is another challenging application with my friends out in Virginia. And trying to measure that kind of flow was very, very challenging. Again, very nothing going on. And then when they have an event, then all heck breaks loose. So challenging location. All right. So let's talk about Laser Flow EX. Laser Flow EX was a NFPA requirement. This one is rated Zone 0, Class 1, Division 1, which we determined from customers that they needed that. A manhole environment is considered that. Now, I will say that some people do risk assessment and may or may not require it, but we now have that. So if you do require it, we can do it. Again, NPF 820 is the rating that it's required. Consultants are going to be more likely to spec these. So we're seeing, the newer group out there, the recent graduates from college are being a little more cautious and complying with that rating. So we are the only ones currently that do a subsurface velocity measurement using Class 1 Div 1 technology. And third-party test results. We did, again, verified that it was not going to lose any kind of accuracy over the standard laser. It has multiple ratings for international, and it's the only one that really provides this rating, again, with this kind of performance. So how do they differ? Well, one thing you'll notice is that the new lasers that are not rated will be blue. So we used a blue color. It's compatible with the 2160 and with the Signature. The Laser Flow EX is now the black housing. It has a easily identifiable label on the side for easy viewing to know that it is truly rated. And for this one, the ultrasonic, instead of being mounted as part of it, is just mounted in the back. It had to be mounted externally. So both are compatible with the 2160 and Signature. The difference would be there's a barrier that goes between the EX laser and the electronics. And that barrier needs to be out of the environment. All right, so what does this thing do that's a little bit different? It uses an ultrasonic, just like the other one, to measure it. In this case, due to the power requirements and restrictions we had, we can only do the 3 points in the middle. So we were a little bit limited on what we were able to do, but for the most part, all the testing we've done, as long as your hydraulics are reasonably good, this method works quite well. And this one is kind of a neat little diagram, kind of give you an idea of velocity profile and what it looks like. And you can see on the surface, it's slightly different than what you see below the surface. So kind of give you a different look on subsurface versus surface velocity. And then dueling laser. This one is kind of neat. We had two lasers in this channel and both reading the exact same flow. We wanted to make sure, again, that we did not lose accuracy with the EX laser. So you'll notice the top pane there is the level. They're right on mirror image. The second one is the velocity. And finally, the third pane in this example would be the flow rate. So they were within 1% of each other. Okay, so to conclude with the Laser EX, it truly is gaining market share and reputation as being a superior performer. The EX now provides you a complete solution for any of your non-contact needs. So if you don't know you need intrinsic safe, you want to play it safe, we certainly have that for you. And it's going to give you very accurate data with very minimal upfront cost and no risk. You don't have to worry that maybe something could happen out there. Okay, so finally, to wrap it up, do the summary. The laser flow is probably the most versatile open channel flow meter that I've ever seen. It's the only one that will read below the surface. Minimal maintenance. We'd like to say no maintenance, but nothing is forever. But I will tell you that we have a lot of them out there that people don't touch and haven't for months and months. So the diagnostics will help you determine if you need to do any maintenance. So if somebody says, how often do I clean it? Well, you should rarely ever have to clean it, but the diagnostic information I was showing you will tell you. So if you have any questions on that, get a hold of us and we'd be happy to go through that with you. With the Signature now, in smart technology, we have a very flexible platform that we're working from. 2100, Signature, and who knows down the road what's coming out. So again, a lot of ways of connecting to electronics with this. And then we have, I think, excellent training and product support. So we have a great product support group out there, and they can help you, determine your application, to determine if it's going to work there or what they would recommend. And we also, again, have excellent representatives, whether they're international distributors or our folks in the U.S. Been around for a long time. We have very, very experienced and well-trained sales representatives for us. And with that, I'm going to go ahead and turn this over to questions and see if you guys have anything that needs to be answered. I'd be happy to answer those now. If you have questions that you think of later, again, feel free to email me at rick.dye@teledyne.com. And with that, I'm going to go ahead and open it up for questions.
Thank you, Rick, for sharing your expertise. We have received a few questions, which Rick and Daryl has also joined him. They both will be assisting us in answering these questions. As a reminder, if you have a question, please be sure to enter it under the Q&A function within Zoom. Thank you.
All right. Well, thanks, Sharon, and thanks, Daryl, for the tag team and assist on this. Most of you probably have talked to Daryl Kuda over the years, and he has a great deal of product knowledge as well as application knowledge. So it's good to have him on here with me. So the first question that I have is pipe size recommendations. So is there a limit to the pipe size? And that is a good one because one of the slides I talk about, we initially designed for large pipe because we knew that was really the market need. There was, it's dangerous. Nobody wants to get into these big pipes. But what we're finding out, though, more and more people are trying to measure very small pipes, and a lot of industrial clients that are doing that. So they might have a pipe as small as even 4 inches. And so they need a way to do that, and a lot of times their flow might be a batch dump, so they have no flow or a trickle of flow until something happens, and then they'll have a bunch of water that comes through there. And the beauty of the laser is where it's looking is dependent upon the depth, but it doesn't matter really what the depth is. So if it can be 1/2 inch and it can be 10 feet, it will position the laser according to where it thinks the peak velocity is going to be. So recommendations, we really don't have any minimal size or maximum, but we have to stay within that 10-foot range of the ultrasonic. So we also have a lot of times where people are trying to measure a 10-foot wide rectangular channel or 20-foot wide. So what the laser is going to see, it's not going to read the entire 10-foot strip. It will read as I tell people, roughly a loaf of bread in that flow. So depending on how high up it is, it will depend on really how wide that beam will be. But if you do have a channel that is, 20 foot wide, you may want to, put 2, maybe 3 on there. I know in the UK, they require, if it's greater than, I think it's 5 foot, they require a couple of them. And the nice thing is with the signature electronics, you can average those readings, you can add them together, you can do a lot of good math with the signature meters. So let us know when you have an application question and what size it is, and and what we would expect to see, and we'll tell you what we would recommend on that. So good question.
Thanks, Rick. This is Daryl. Along those same lines, another question came in about how wide of a manhole do you need to install a laser? So it needs to be wide enough that you can actually get a person down there to install the mounting bracket. So once it's installed, you can use that extraction tool and pull it out. But initially, somebody will have to get in there to mount the bracket to the wall or use our spreader bar to install it. So with that, you're going to need at least 24-inch wide manhole to be able to install the laser flow sensor and bracket.
Okay, yeah, good question. Also, though, along those lines, if they're using a temporary mount, do you know, Daryl? I can't remember, but what is the maximum we can go on that?
I know the minimum is 4 feet, and then I think it extends out to about 6 feet.
Okay. All right. Well, good question. Here's one. How good would the laser sensor work for an RAS channel of 6,000 milligrams per liter? That is a good one. There really is, people ask us how clean, how dirty can we read? And for the most part, we can read on the clean end, we've read tap water, and we do that with our trade shows. That's what we use, but we are pumping it. So there's some entrained air in. Any Doppler device is going to need some reflectors, including us, to be able to read, return signal. The beauty of the laser is that it can read, because the signal is so clean, we don't need as much particle or as many particles in the flow as you would with a standard area velocity Doppler type sensor. So our spec is, I believe, 15 parts per million. But there's times where people on effluent of plants are way, way cleaner than that, and we read it just fine. On the heavy side, we have sites where it's coming right into the wastewater plant, might be real deep, things like that. We will know when we look at the diagnostics, we will know immediately with that Doppler signal or Doppler shift. If we're not getting anything back, we will be able to see that in the diagnostics. And there are some adjustments that we can make to minimize the effect of extremely thick or nasty water. We have had these in mining applications too, where, worst case, we'll read closer to the surface and we can still read that. So a lot of flexibility and capabilities as we go forward. And since 2013, we came out with this, we've really learned a lot and learned how we can make this amazing tool work in some of these applications. And so that's why we're happy to kind of present that to you guys today. So anyway, let us know. And, bottom line, put one in, give it a shot, see what it does. And we can help tell you, yep, it's going to work, or no, it's not, immediately.
All right. Our next question is, what is the minimum flow required to have the accuracy error you mentioned in the presentation? So the accuracy was within 4%. And so the minimum velocity, it would be a half foot per second with a half inch of water depth. We have used the laser in applications that have had even slower velocity, down to 0.25 foot per second. But as far as our specifications that we've tested at the Alden Labs and other laboratories has been down to 0.5 foot per second.
Yeah, and the tests that we did, the Alden Lab, again, the guys out in New Hampshire did a great job, but they ran it, I think, on the 36 or 30-inch round pipe. So that was one application that we ran it on. And then we ran it on the one in Cal Poly San Luis Obispo in California. That was on, I think, a 5-foot rectangular channel. Mm-hmm. And so we had two different looks, two different applications. And, we were able to tell immediately if they were going to work very well or not. And we saw that they did. We are looking at a peak velocity times the USGS coefficient of 0.9. To calculate the average. Now, we're not big into adjusting things, but if you do need to adjust it because maybe I have a weir wall downstream and my hydraulics are not free flow, we can adjust it. You can tweak it to match what you think it should read. We're, again, not big fans of that, but sometimes the hydraulics and your condition may dictate that you have to do that. So anyway, good question.
All right. Hey, thanks, Rick. We've got another one that came in. You had mentioned that when the laser's on, for 2 seconds, it takes 5,000 samples. And what they wanted to know is that if they were recording an output every 5 minutes, would it take an average over that 5 minute duration? And I'll take that. So yes, what it will do is it will average all the readings over that 5 minute duration, and the laser on average comes on about every 15 to 30 seconds. And so for the easy math on that, we'll say the laser's on every 30 seconds. 30 seconds it turns on. It's on for 2 seconds, takes 5,000 readings. And so over that 5 minute period, we'll have 10 individual readings that it would average all those for the time-stamped logged reading. But you can, with the signature meter and the 2160, record as fast as every 15 seconds if you want to. So you can go 15 seconds, a minute, 5 minutes. So it's kind of up to the user.
Hey, thanks, Daryl. Here is one: is a special flume needed for very low flow situations? That is a really good question, because we are seeing a lot of low flow applications. And the answer to that is no, you do not need to dam up the flow. You don't need to back it up like we have in the past with some area velocity technologies where we weren't above an inch. So people would put some kind of damming device downstream to build the level up to get above an inch for the velocity to turn on. And we're actually the opposite with the laser. We don't want anything in there. So if you have a flume, you want to stay, as far away from the converging section or things like that. We're same thing. We want to stay away from those. But if you can remove that or put it in a application where you don't have the flume, that's the way to go. We are working now with some pre-treatment groups, and they are looking at, okay, we have challenging applications. They don't like the flumes. A lot of the flumes aren't installed right. They're outdated, they're undersized, oversized, whatever. And so they are now requiring, instead of them putting in a metering manhole with the flume, they're going to go with just metering manhole with a straight pipe going through, like the picture I showed earlier, with the just a cutout in the top. And if you can do that cutout in the top with a round pipe, you have perfect hydraulics, good straight run, upstream, downstream diameters, and you're good to go. And the laser will read, I've seen it read down to a few gallons a minute. So we don't recommend that you put anything in that flow to dam it up.
All right, we got another question that came in about power. And so the question is, what can be used to power the systems? And so with the laser flow, we've got a couple of different options that we're quite flexible. So, we can run off of 240 volt, 120 volt AC, or a battery or solar panels. So depending on your application, you can run off a solar panel, and then tie that directly into the 2160 portable unit, or even our signature meter. We've been using that a lot for portable applications. That way you still have your local display, and then we can power that off of 12 or 24 volts DC.
Okay, alarming in software. Okay, so the question is, can we alarm off of diagnostics? As you know, and those of you that have heard me before, I'm big on the diagnostics. I want to know when I get a reading if it's a valid reading or not. The answer is yes, we can alarm off of anything the meter reads, whether it is a 2160 or a signature flow meter. If it reads level and you want to set a high alarm for that, you can set that. If you wanted to do low signal strength or low velocity, surcharging, whatever, you can alarm off of any of those from the site. But one thing that I should point out, and we didn't really hit on it today because we've already done a webinar on this, is FlowLink Cipher. And FlowLink Cipher is our latest introduction to the market on software. It's a cloud-based program. I'm not going to harp on it too much today, but if you have questions on it, let us know. But what that will allow you to do is have data pushed to the cloud. So now it's in an Amazon server. We can set up alarms from the server, which we were not really able to do before with FlowLink Pro and some of the other stuff. So FlowLink Cipher, if you haven't seen it, send us an email. We'll be happy to send you some information on that. But that is going to tie really all these alarms and diagnostics and everything together in a nice package when you're doing remote communications. And I can't really stress it enough to say, everybody's doing more with less resources. And if you can put something in that's non-contact that you don't have to do maintenance on, and it's going to be accurate and maintain its calibration, and then you could do remote communications and get the data on the cloud without involving a lot of IT work, really is going to be a great way to go, and we think the way of the future. So good question though.
All right, Rick. Well, looks like we're about at the top of the hour here. If anyone has additional questions, you can feel free to email Rick Dye or respond to Sharon, and she can get those questions over to us.
Yes, and we'd like to close by saying, thank you very much for attending, taking time out of your day. Hope everybody's staying safe, and look forward to hearing from you and getting through this COVID-19 deal and moving on to next year. So give us a call if we can do anything to help you, or do any kind of presentations for your group. If you want to do something like that, we can certainly do individual company webinars on software, flow link, the whole bit.